So for example, for letter A, for this integral, we have the integral from 1 to 4 of dx over the square root of x minus 1. All right, so let's look at the graph of this function. Well, I'm going to give you the graph, and notice that the domain for this function, we cannot have either -1 or all values less than, 1 or less. And that's actually going to be represented by a vertical asymptote in this case. So we're going to have a vertical asymptote at x equals to 1, and it's going to look like this. And in this case, we're integrating from 1 to 4. Well, notice in this case, the lower limit of integration is the actual discontinuity in this case. So for this reason, we need to set this integral in the form of a limit problem. Because yes, we're going to approach, in this case, we need to be very specific with the limit, because so that's from, let's call it just from t to 4, as t approaches 1. However, we need to be very specific with the limit, because we are only approaching from the right. All right, because there's really no graph, number one, there's no graph from the left of the asymptote, and we are not integrating somewhere in before this vertical asymptote. So dx over the square root of x minus 1, or rather, well, let me do square root of x minus 1. You know what, let me change it to rational exponent, x minus 1 to the 1/2, and then limit t approaches 1 from the left of the integral of x minus 1 to the -1/2 dx from t to 4. Well, in this case, we can just use the general power rule. To be honest here, we really don't need to show a u du, because u is x minus 1, du would be just 1 dx, and there's really nothing weird to change over here. We can just go straight to the integral, and that's going to be x minus 1 to the -1/2 plus 1. That's going to give us a half. And divide that by 1/2. And that evaluated from t to 4. This means, well, we keep the limit. And that's going to be, well, dividing by 1/2. Isn't that the same as multiplying by the reciprocal, which is 2? And I'm going to have it outside of the limit, so we don't deal with too many calculations here. Well, and then I'm going to change this x minus 1 to the 1/2 as the square root of x minus 1, still evaluated from t to 4. So then from here, well, let's use again the fundamental theorem of calculus, and that's going to give us the square root of 4 minus 1 minus the square root of t minus 1. And well, the first quantity, 4 minus 1, that's 3. That's just going to be the square root of 3. And in this case, let's have a look at this limit. Well, in this case, we want to approach 1 from the right. All right, we want to approach 1 from the right. Well, actually, no, not from this graph. Never mind. So simply, 1 minus 1, that's going to be 0. And that's 2 times root of 3 minus 0. And final answer is 2 root of 3. Okay, so in this case, because we got a finite number, even though it's an irrational number, doesn't matter if it's an irrational, rational, decimal, as long as it's not an infinity, the limit is not infinity or dne. Well, in this case, the integral converges. All right, the integral converges in this case. So again, we don't have infinite limits of integration this time. We have rather discontinuous limit or rather interval of integration, because in this case either one of the limits, whether the lower or the upper limit, could be in this case one of the discontinuities, or we're going to have a discontinuity somewhere in between the limits of integration, which in this case it's going to be the second integral. So let's have a look at the second integral. We have the integral between 0 and 5 for the function f of x equals 1 over x minus 3. So number one, if we look at the domain of this function, notice that the function won't be defined for x equals to 3. And if we notice that x equals to 3 is contained between the interval 0 and 5. So in this case, we are going to have the discontinuity somewhere in the, well, not exactly in the middle, but I mean somewhere in between the limits of integration. Well, so how about we draw the graph of this function? Well, so so in this case, let's represent the vertical asymptote at 3. And the graph of this function will resemble that of f of x equals 1 over x, which usually looks like this. We have the two tails pointing to different directions, but in this case, this minus 3 in the denominator is telling us to shift the graph 3 units towards the right. So it's going to look like this instead. So ultimately, what do we want? We want the integral, or the area under the curve, from 0 to 5. We want that shaded area. Let's see, what about it? So this integral, however, we will have to split it into two integrals. And the reason for this is because of the discontinuity in between. So how about we relabel this as this part to be I1, which is the first integral, and this to be I2. These I1 and I2 are going to be, number one, the integral from 0 to the location. The upper limit of the first integral will be the location of the discontinuity in this case, that is from 0 to 3, dx over x minus 3, plus the integral, that's going to be I2. We're going to start from 3 to 5 in this case. Alright. So, what would be next? Well, the next thing would be here to, and be very careful here with the limit notation that we're going to use for these two integrals. So we're going to represent the first integral, the one from 0 to 3, as a limit of the integral from 0 to 3 dx over x minus 3. However, notice we are approaching the discontinuity. In this case, from which direction? We're approaching this from the left. Yes?
In the second part of the addition, why is the denominator change to x minus 3?
Oh, no, I don't know why. Yep, should be 3. Thank you. So in this case, we're approaching t to 3, however, from the left. All right, because we're approaching that asymptote from the left. And on the other hand, we need the integral from 3 to 5, dx over x minus 3, t approaching also 3, however, notice the approach is from the right. Alright, other than that, I mean, I think this is going to be the usual integration rule. So number one, let's do one of the integrals. Let's call this again I1 and I2. So let's evaluate I1. I'm going to do I1 first. So for I1, we're going to get the integral, okay, limit of the integral from 0 to 3, t approaches 3 from the left, x minus 3 over x minus 3. Well, no need to do any use substitution in here because that's 1 over x minus 3. So how about limit of ln of absolute value of x minus 3 evaluated from 0 to 3 as t approaches 3 from the left. Alright, so let's plug in upper limit minus lower limit. Limit t approaches 3 from the left, ln absolute value of 3 minus 3, and minus ln absolute value of 0 minus 3. Now, here is the issue here. There's the issue here. So in this case, we're going to get ln of absolute value of 0 minus ln of absolute value of negative 3. Well, ln of absolute value of negative 3, no worries, that's why we have this absolute value to turn it into a positive so we can evaluate the natural log. However, what's the natural log of 0? I think it's the reverse. It would be e to the 0 equals to 1, that's the inverse function. But ln of 0, what was that again? Yeah, not in determinant. Well, so okay, how about we draw the graph of ln f of x equals ln of absolute value of x minus 3. Alright, so in this case we can do the graph right here. We have a vertical asymptote for the natural log function. So usually this is represented the following way. Usually the graph of natural log looks like this. Alright, however, because we have absolute value bars over here, this means that this function can also take negative values, but also that means we're going to get the other side of the graph. Now we are approaching 3 from the left. I mean from the, did I say left or the right? Or from the left, never mind. From the left. So where are we going here? Negative infinity. Alright, that means that our integral blows up to infinity, so the integral converges. I mean diverges. So the integral diverges. And well, notice in this case we split the problem into two separate integrals. The minute one of the two integrals diverges, no need to bother and do the second integral, because even if the second integral converged, here we already have some negative infinity, so a limit that does not exist, so that means the integral diverges.
Is there a reason you're evaluating
0 to 3, because in this case we need to split the integral between, well, the lower limit and the value of the discontinuity, plus the second integral goes from the value of the discontinuity to whatever upper limit.
But why is it not 0 to 2 instead of 0 to 2?
Oh, well, that's true, right? So that's 0 to t, that's true. I see what you're saying. Yeah, let me fix this to then t, and that's t actually, yes. Yeah, you got this. Yeah.
When you say integral diverges, is that assuming that you can't find the area?
Exactly. Well, actually, it's in infinite area. So the value of the integral, well, it's the area under the curve. It's really big. It's infinity. So in this case, diverges. All right. Okay, what else do we have for improper integrals? So we're going to look at something called the P integrals, and this is going to get us started to chapter, oh yes, question mark? No need to do it because, I mean, even if the second integral converges, we already have one part that diverges, for example. Even if I2, let's say it's equal to 5, this one is already equal to negative infinity. So negative infinity plus 5, I mean, it's still infinity. So no need to do the second one, which is great. That way you don't have to spend a lot of time doing this. All right, so P integral. So that's going to get us started into infinite sequences and series for later when we get to that chapter. I believe it's chapter 11. So up to this point, you might have noticed some patterns about certain integrals that converge and certain integrals that diverge, you know. So let me see if I had something that diverge. Well, so no, not really. So anyway, so here, whenever we have an integral of the form 1 over x to the power p, all we have to do is observe that value of p. On the one hand, if the value of p is greater than 1, is strictly greater than 1, well then all we say is that the integral converges. But otherwise, if the value of p is less than or even equal to 1, we just say that the integral diverges without even performing the integral. In some cases, we need to perform the integral. Well, it will depend on instructions on a quiz or an exam, or even on the homework, like just actually evaluate the integral or just use the P integral definition to determine the convergence or divergence of the integral. All right. So let's see. So number 1, for the first integral, the integral from 1 to infinity of 1 over x to the 7. Well, without doing the integration, all we have to do is identify the value of p. So in this case, for this one, p equals to 7. Now the question is 7 greater than 1 or less than or equal to 1? It's greater than 1. What does that mean then? Integral converges. All right, just like that, without doing the integration. Let's see, the integral of 1 over the cube root of 3 from 1 to infinity. Well, number 1, we need to rewrite this integral in the form 1 over x to the p power. In this case, well, we have it in radical form. But in this case, what we can do is simply rewrite the integral as a rational exponent. That's x to the 1/3. Again, the index of the radical will tell us about the denominator of the rational exponent. Well, so all we have to do is identify the value of p. And in this case, p equals to 1/3. Now, is 1/3 greater than 1 or less than or equal to 1? So less than or equal to 1, right? This means then that the integral diverges. Right? Letter C. Integral from 1 to infinity of 1 over the 4th root of x to the 5th. And again, we need to rewrite this in the form of rational exponent. That's the integral from 1 to infinity dx over x to the 5/4. Now, let's observe this. So the value of p in this case is 5/4. Now the question is 5/4 greater than 1 or less than or equal to 1? It's greater than 1. That means integral converges. What about the last one? I mean, just by looking at the last one, the integral of x cubed dx. Well, what's going to happen when we integrate that function? Well, we're going to get a function that is higher in degree. That is going to be x to the 4 power over 4, which is going to make actually a bigger infinity than we already had, right? So that's just by looking at the integral. However, in order to make this integral look like the p integral form, well, I would rewrite this integral in the form of 1 to infinity dx over x to the negative 3. And then in this case, p equals to negative 3. Now the question is negative 3 greater than 1 or less than or equal to 1? Less than or equal to 1. What does that mean? Diverges, all right? So, integral diverges in this case. And the last topic in this section about improper integral is the comparison tests for improper integrals. Well, so here this is what we're going to have. We're going to have two integrals. One integral is easy to observe about, or it's easy to determine its convergence or divergence by just looking at the integral, and that's going to be the test integral. And on the other hand, we're going to have a problem integral that it will be impossible to integrate with the methods that we know. So in this case, we're not looking at the methods of at actually computing the integral. We're using the information of some other integral that behaves similarly, and it has some similar looks. Compare, and from there just decide, oh, this integral converges because the other integral converges, or diverges because the test integral diverges. So in other words, so let's label this as our test integral. So when it comes to convergence, this will be our test integral. Something that for sure we know that converges. And when it comes to divergence, we need to say, in this case, it's also our test integral. All right? So this is what we have to do. G of x, which is our problem, has to be less than or equal to f of x. Okay, and well, in this case, this should be the condition for convergence. So converges if this is true, but otherwise diverges if f of x is greater than or equal g of x, which is in this case our problem integral is an actual bigger infinity than we already had. Well, right now it's like a lot of symbols and a lot of ideas. I guess doing a couple of examples, seeing this in action, it's going to make more sense. Alright, so for example number 7, they're asking us to show that the integral from 1 to infinity, it's a convergent integral. Well, they're giving us the answer. Our job here is to actually show that this converges. Well, so how about we come up with a new integral that it's easy to determine its convergence, right? Well, so here is the thing. This integral looks like the integral from 1 to infinity of e to the negative x dx. All right? So in this case, it looks like e to the negative x dx. Well, so what do we know about this integral? Well, this is the integral of an exponential, of a decaying exponential function. But in this case, we're integrating from 1 to infinity. This should be a convergent integral. In fact, even if you want to do the integration, well, limit from 1 to b approaches infinity, e to the negative x, dx equals negative limit e to the negative x from 1 to b, as b approaches infinity. And then just upper limit minus lower limit, that's a negative limit b approaches infinity, e to the negative b minus e to the negative 1. So in this case, well, this limit is going to go to 0, and negative times a negative is plus e to the negative 1. So the integral converges. Now, if you prefer to see this as a picture, well, this is the decaying exponential function, and we are actually integrating towards positive infinity. Do you see how in this case we're converging somewhere as opposed to integrating towards a negative infinity, in which otherwise we would have gotten an infinite area in this case, and which means that the integral diverges. Well, so in this case, how are we going to set up this proof, or this, well, how are we going to show this? So in this case, they're telling us convergence. So to show convergence, need to show that g of x equals, is less than or equal f of x. Alright? Where g of x is our problem and f of x is our test integral. Something for sure we know that it converges. Well, so in this case, this is our g of x, and this is our, well, actually, use a different color, g of x, and this is our f of x. Well, so in this case, putting these two together, g of x, which is e to the negative x squared, is less than or equal e to the negative x. Is this inequality true? Well, if at first glance doesn't look like it is true, change these to positive exponents. And, well, observe the denominator of the left-hand side. Because of the x squared, that's going to give us larger numbers in the denominator, which is going to make this side smaller than that side. Alright? So in this case, what are we essentially doing when we are comparing integrals to show convergence? In this case, we need to show that tiny is less than or equal to small. So that's how we're going to compare integrals that converge, and to show that something like this integral is also convergent. And the reason why we're using this this comparison theorem, this comparison test rather, it's because this integral that we have right here of e to the negative x squared, we cannot evaluate it with the methods that we know so far. If we try, for example, u substitution, we're missing a factor of x that stands the u du function. However, we're going to learn how to integrate this function later when we get to power series and infinite series and representing that function as a polynomial. Well, you'll see when we get to that section chapter. All right. So for example A, now they're asking us to show that the integral from 1 to infinity of 5 plus e to the negative 2x over the square root of x is divergent. So now they're asking us to show otherwise. And in this case, we need to be very careful. So our test integral is going to be our g of x, not our f of x. And well, in this case, so if we try to evaluate this integral, 5 plus e to the 2x divided by the square root of x, don't even try. nothing is going to work. Neither integration by parts, and I don't think there's another method that could work in this case. However, we are going to find an integral that looks similar, for which it's easy to determine its convergence or divergence. In this case, well, so how about how about if we compare this integral? Let's pretend we don't have the numerator. So it will look like the integral from 1 to infinity of 1 over the square root of x dx. And in this case, we have to compare it with an integral that for sure we know that diverges, not with another integral that converges, because otherwise the test will be inconclusive, or it wouldn't be a valid test, or it wouldn't have any logic, of course. So, and well, without doing the integration, which is what I did before, how about instead we do the p test. In this case, p equals to 1/2. And well, we know p is 1/2, which is in this case less than or equal to 1, so for sure this integral will diverge. Alright, diverge. So this integral will be helpful to check to show the divergence of the given integral. Now, to show divergence, need to show the following. Need to show that f of x, or actually g of x, is instead the reverse, actually greater than or equal to f of x. Well, what's our g of x? Well, our g of x in this case will be the problem, and this is our f of x, our test integral, something that we know for sure diverges. Let's put this together. So g of x, which in this case is 5 plus e to the negative 2x over the square root of x, is this inequality true? Is this quantity bigger than that quantity? I mean, the denominator is always the same. But for large values of x, I mean, even though we have this e to the negative value, which will become very tiny when for large values, but this 5 is always larger than 1. So in this case, that's good enough to show the divergence. So what are we showing essentially here? So we are showing that huge is greater than or equal to big. So again, in summary, to show convergence, we need to show that tiny is less than or equal to small, and for divergence, we need to show that huge is greater than big. So essentially, we are testing this integral both diverges, but this integral will diverge more than something we are comparing it with, and we know that it's going to to diverge more, if you will, because of the form of the expression that we're integrating. This quantity will always be for sure bigger than that quantity. Alright, so let's see. I think this actually finishes the section. So let's move on quickly to the next section. And the next section is the arc length. I don't know if I'm going to have time to do this derivation. Well, hopefully I will. Well, so arc length, that's another application of integration. And well, so let's draw a picture real quick. So we have a function f of x, and we want to find the arc length. That is, in this case, the distance that we travel along a given curve from the point A to B? Well, so this is going to be based on the distance formula, and somehow the Pythagorean theorem will be involved. But the question is, okay, let's construct this idea first. So number one way to go from point A to point B is by just connecting the 2 points like this, right? So, however, that's not going to be the actual arc length, because look at all the distance that we're not considering. So that's not going to be the actual result. Let me actually make this a lot better. So let me erase this point, and I need this one instead. Okay? So there's another way to go from point A to B. I'm going to do A here. So another way is to go somewhere here and then over here. I mean, the distance is getting closer to the actual value, but still not quite, right? Still not quite. So how about we do another way instead? How about we go like this? This distance, that's distance, and that distance. Okay, stepping at 1, 2 point. Well, it's still not quite the arc length. However, it's kind of getting closer to what we want to obtain. Well, what am I trying to do? What I'm trying to do is like doing a partition. So you might remember from the area under the curve between A and B, the first time you define the area under the curve, which is the integral, what did you do? Partitions by rectangles, in which, well, depending on the number of integrals, like 3 integrals, well, there's some area left out. And then what we did in Calc 1 is to make a refinement to pretty much infinitely many of these rectangles that will give us the actual area under the curve. So we're going to do something similar to construct the idea of the arc length in this case. Well, so in this case this is not going to work. So how about we go like this: 1, 2, 3, and 4. See how it's getting closer to the actual arc length? Alright, well, of course we don't have time to do infinitely many refinements in this case. In fact, well, it's not going to be possible. So this is what we're going to do. I'm going to do just one random. I'm going to take just one random arc length. And in this case, notice this is, let me label this as L. L sub I. The subscript I in this case will represent just any random length. For example, if we divide this into 100 mini lengths to get closer to the actual length of the curve, well, I can choose the first one, the second one, the third one, doesn't matter, the ith one. Now, in this case, think of this line right here to go from this point to that point actually requires some motion in the x direction and some motion in the y direction. In this case, well, how about this change in the x direction? Let's call it delta x sub I. So that's an increment or some change in the x direction, and let's call this delta y sub I, right? What is this? Isn't that just the Pythagorean a right triangle? Okay, so let me write that right triangle a little bit bigger. So that's L sub I, delta x sub I, delta y sub I. Well, so using the Pythagorean theorem, which we know that's c squared equals a squared plus b squared. Well, c squared would be L sub I squared plus equals delta x sub I quantity squared plus delta y sub I quantity squared. Well, what are we going to do from here? Well, we want to solve for L sub I because we want the arc length L. So in this case, L sub I equals the square root of delta x sub I quantity squared plus delta y sub I quantity squared. All right? And well, in essence, this is what we're going to use as a starting point to derive a formula to find the arc length given a function f of x.